Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today, we will start with a new topic which is on deep visual learning, which means that using the learning mechanism to solve the problems of visual processing. So, first let us understand what is meant by deep learning. Now, this word deep came from the fact that when you are using a neural network model, in the previously we discussed also that using machine learning techniques where using artificial neural network, you can build up a model to solve classification problem. But what happened that previously we have only a few layers of processing because of several constraints on the computation power resources we had, and also the kind of labeled data set, the size of the data set, that also was not sufficient to go for a deep model or a large model. But now, since we have the large data set and also the computational power has been increased to a great extent because of the advancement of the technology. So, we talk about this kind of deep neural network which has a very quite a good number of layers in its model. So, in the classical model, as you see that in a neural network we have input to the model, and then of course there is an output from the output layer, and only a few hidden layers there in this model. Whereas in the deep neural network, we can have a number of layers. We can have many hidden layers. It could be as many as few hundreds also. So, what are the problems that we solve using this kind of deep learning mechanism? We solve the same kind of problems earlier, like object recognition or classification, but with much higher accuracy. And above all, we also solve many complex problems which we are not able to solve previously using simple, I could say shallow artificial neural networks. So, the problems like object localization. So, this is one example how the corresponding output would be there. Given an image, you can see there are several boxes which encloses an object. Not only that, it identifies those positions, that is object localization, but also it also predicts the class of the object. For example, there is a cycle, there is a car, there is a dog. So, those prediction, it is possible. Then there is also another kind of dense prediction of each pixel, which is called semantic segmentation, which means I will be segmenting out this object. So, here roughly we are saying that within this box we have the dog, but in the semantic segmentation exactly we can get the respective contours of the pixels belonging to the dog, and it will just mention that okay, this is the area where which belongs to the class dog. Similarly, you consider other classes which are present. So, that is why semantically associated. So, it is a kind of dense prediction. Every pixel is being predicted to some class. So, here is another example. You can see an image where there is a bus and also there is a car. So, in semantic segmentations, we get the pixels associated to the bus and associated to the car. So, that would be the final output. We call it not only segmentation, but also we label the pixels of that segmentation. We get the semantics of those segments. Then, of course, these techniques could be, there are various techniques related to video processing, like video summarization, tracking of objects. All these things could be solved using deep learning models. Many other problems could be solved. So, the question, as I started by saying that deep architecture, why it's so late in application? As you see that essentially it is a neural network model. The concepts even for different kinds of processing, those are also present. Those are also earlier thought about and also introduced in 80s itself. So basic principles remains the same. But there are two major reasons for the phenomenal growth of this kind of technology and solving the problem with a very high accuracy, so that now it is getting applied in our real life applications. So one of the factor is that availability of large scale annotated data. So when you are using deep learning models, so you should see that data set is quite rich, quite large. So that is one thing. And second thing is that advancement of computing power, because you require parallel computing power to train the model. As you see that we will be using optimizations of the neural networks, and if the model is very large, then computing the gradients of that in the parameter space itself very expensive. That backpropagation algorithm what I discussed, if you consider there are millions of parameters, it will take so much of time. So, but there are advancement in computing architecture, computing infrastructure. So, by which whatever earlier we could not have computed would have taken years theoretically. Now it could be, you could take a few hours maybe, and sometimes it could take weeks, days, but it is tractable and it is manageable, and you can get a model with a very high accuracy to perform the task. So, just to mention that the key factors because of these millennium, the start of the millennium itself, we know that internet has penetrated, smartphones are being used. So, there are also widespread of social networking and online shopping. So, the data in the form of text, images, different kinds of multimedia modalities, those are hugely available. There are repositories. And then you require annotating, of course, those data. That is quite expensive, but still there are methods by which one can do. And if you do the annotations, first the material conditions, the data is available, then you employ your labor to get the annotations or use some kind of techniques to get the annotation done, a bit semi-automated techniques, and then you have a rich data set, and which could be very large. So that is the reason, as I mentioned, that you can consider complex models or large models to solve a problem. And advancement of computing power, particularly we have this GPU computing. And in GPU computing, you can train the network much more readily or with a tractable time, though it may take few weeks also in some cases for a bit large model. So, what is the difference once again between the classical image classification problem and these deep learning models? So, there is also a difference. It is not only that you have a large neural network, but essentially approach wise also there is a difference. So, if I look at this classical image classification problem, which I just discussed in a previous topic, you consider, for example, this image, which is an image of a tiger, or you want to classify this object. Now, when we are going to classify the object within this image, we have to do certain feature extractions. But these feature extractions, we try to design a priori, that we relate the object classes with tigers. For example, in tigers, maybe we consider the shape of this mouth is is one of the very distinctive feature with respect to other animals. Maybe you have to consider also what is your domain with respect to other objects. Then you can consider texture, color, the stripes in the mouth, in the face, and the kind of I should say different kind of sub objects presence. All those things, it makes a distinctive mark. But how to translate them, how to get them into a form of a feature vector so that it reflects those characteristics, that is interesting, and that is what one needs to do analysis. And for example, the edges, maybe the contours, geometric contours, textures could be represented. I discussed various such techniques earlier. and people try with different kind of statistical methods to associate with these features with the classes, and finally once the features are selected, then you train the model. So feature selection, feature engineering, it is done a priori before training the model. So what we do, we call it handcrafted feature extractor process. The term handcrafted doesn't mean you always do manually, it is computed, but no, you did analysis and then no, you considered this is the step, you have designed the algorithm for feature extraction, and then you apply the algorithm and then you convert it into a feature vector. So as I was mentioning, many of the feature vectors representations we discussed, some of them are typically shown here. And then use the classifier algorithm to train the model. And there are different kinds of classification approaches we also discussed: Bayesian, LDA, SVM, KNN. And finally, you get the class assignment as the output. So this is the classical approach which we discussed also in the previous lecture. And you know that classification problem like this. So, but the thing is that as you understand that there are limitations with these approaches. First thing, it is very tedious and costly to develop this kind of handcrafted features. And also there are various challenges on the various variations on the images itself. I will show you a few of these examples here. Just you can see that there could be viewpoint variation, there could be deformation, occlusion, intra-class variation. So you can see that intra-class variation, there are white tigers, there are yellow tigers. So there are variations on that. And then the image could be badly illuminated, and there could be clutter, means the object is there, but there are presence of dominant many pixels are of different other classes. Now if you want to detect the tiger, so it would be difficult on that kind of background if it is not very dominant object in the scene itself. Then there are different instances also. There could be multiple objects which are present here. The scale is another problem which we discussed, that you take the image from the closer distance, closer viewpoint, or you take the image from the remote end. So this kind of variation should be there. So considering this classical approaches, they usually don't work to handle all these variations. They are severely constrained with certain assumptions. So it highly dependent on one application and not transferable easily to other applications. Now, when we consider classification through deep learning, we rather here in this case, the first difference is that we do not go for any kind of feature engineering or analysis for the task. Rather, we leave it to the model itself. So model itself takes care of to learn the feature extractor, and then those features which are extracted, those are used for in the classification. So the whole thing, it is basically done at the end-to-end fashion itself. So you have so in that case, the model has to have some kind of uniformity in the architecture, and we use the neural network. We will see how we do it. So we say that part of this neural network, it is meant for learning the feature extractor, and then there is a stage of classification. So you have the input and then you have the output. So the whole thing together makes a model, and which is a deep neural network model. So now your parameters are, and it's an end-to-end fashion. So you have been given only input-output specifications, and you try to optimize these parameters in such a way this input-output specification gets matched. And while doing these things, you know that actually those features are extracted, appropriate suitable features are extracted as per the specifications what is given to you. So from the data itself, everything is learned. So this is the major difference of the approach in the deep learning based approach. So you know that even the features can be described in different, extraction can be guided through different levels of extractions, like low level features, then mid-level features, then high-level features. And so this feature extraction can go through also several stages. And finally, you represent them, all these features, whatever form you, in your model, you represent them as a single feature vector for that object, and then make it an input to a trainable classifier, and then you also training that classifier to get the output. So one of the major distinction here, you are learning the filters of feature extraction. So you'll see that why we are saying filters, because in the neural architecture framework, these feature extractors are nothing but some kind of filters which are performing convolution on the images. As you know, all these features, they also can be considered as a response of a filter, and which are extracting edges, which are extracting certain texture patterns, etc., like low pass filter, high pass filter. So essentially, they are performing certain convolution. So what you are learning the impulse response of those filters, or we call it filter weights, or we call it kernels. So different terms, but these are the things we are only learning. So you will see that those parameters of the neural network, they are actually some of these filter kernels. They define those filter kernels. And of course, at the end, when you are training the classifier, that is some kind of once again feed-forward, fully connected neural network, where those weights are also trained to perform the task of classification. So this task, as you see, the deep learning, what we are discussing here, we are discussing under the supervised learning framework. That is the first thing. Though your network may also take unsupervised tasks, but in this case, since we are discussing about the problems, whatever we have discussed, they are mostly supervised learning, because the data set, annotated data set, we consider which we have X is the data and Y is the level, and set of such data we have. That means it is not only single data. You should have a large data set, various instances of the data. And your objective is the same as to learn a function f to map from your data to the level. That means given any unknown feature vector which is representing a particular object in that space, we would try to find out what is the functional value, which could be a class, which could be a regressed value, etc., which could be also the position of the object within the image, various things. It could be the caption of the image. So your levels could be different. So it's a very general framework, but in all such cases, it is assumed that you have the labeled data set, and by which you are training a model. So just to summarize that, what are the steps of this supervised learning? What are the components? What are the features of the supervised learning? We consider the first step should be to define the model. Like artificial neural network architecture, that defines the model. And deep model means the architecture would be deep. There would be more number of layers. Anyway, so in an mathematical abstraction, so we can consider it's a function of x, which is the data, and its parameter w, and they represent that function, and you are trying to map it with the corresponding level y. So this is input data like image pixels or images. These are the weights, and this is the model structure, and this is the predicted output or image level. So your objective is to learn a parametric function f composed by weight parameters w to classify image x as class level. So then naturally you have to form this data set. So collection of data set is very important, which is non-trivial, but as I mentioned that because of the technological advancement, now large data sets are also available. There are many repositories of large data set. Then the task of learning comes, which means you have to train the neural network, and there are some loss function based on which this training is taking place. So you define a loss function, which is considered here. The whole thing is a loss function, but there are different components of this loss function. Now, this loss function basically it says that this component in this case, it is basically it is a loss of between the prediction of the output and yi, that is a true ground truth. So, what is the difference? What is the difference between predicted output and the ground truth? So, that is the loss function we consider, or that is the error function. Loss function is same as the error function, and there is a regularization term. So, this loss function measures the badness of prediction, the first component, this component, it measures the badness of the prediction, and this term is called regularizer. Now, this is introduced because we try to prefer the smaller size model than the larger size model. This is the principle of parsimony of scientific approaches. That is what we are guided by that principle. So, here this regularizes, it penalizes complex. So, if your model size is large or if your model weights are very large, that becomes a penalty. So, if there are smaller size models or smaller values of weights are there, so we would be preferring them with comparable performances. And we are of course taking the average over the whole batch of training samples, and you know that your objective is to select that W, choose that W which will minimize this error, and we are expressing by this functions argmin, which actually gives you the value of W where this function becomes minimum. So this is the task, this is the computational task that we perform when you learn the model. So finally, this is the learned weights. So once again, as a summary, as I mentioned, there are two types of losses here we mentioned, like data loss and regularization loss, and they are used for these things. So some of the cases of loss that would be data loss would be that you predict the models, it should match the training data, and one of the kind of loss we have already considered the least square, the squared error method, but we know that squared errors are mostly good for regression purposes, that is functional values. But in this case, as you have seen that these are discrete class values, so rather we go for the probabilistic approaches. So we compute the probability of a belongingness to that class. Actually, posterior probability, we compute the posterior probability, which is given by the softmax loss, and it is computed in this fashion. Suppose you have the corresponding, these are the output, say this is the architecture, neural network model, and this is your input, and in your output layer we have the respective output node, from where you get the corresponding levels. We are saying, say SY1, SY2, so similarly this is say SYM, if there are, let me put SYK, if there are K classes. Now, these are the values, and we assume whatever values you are getting from the network. So, we convert this vector, we convert these values to a probabilistic, in the probabilistic interference which we consider as the probability of posterior probability. That means, what is the probability that this says this node corresponds to, say, class, say omega 1, say this is corresponds to omega 2, and like that. So, what is the probability of class 1, class 2? Let me say like this. What is the probability of class 1? And this is we consider this is actually proportional to the logarithmic value. We convert it into to get the probability, we are getting the log likelihood values here, or logarithmic of the posterior value. So, this is what we assume we are getting. So, if I perform these operations, we make the exponentiation of these operations and then take the log, then that would give you, this log is different, this is for cross entropy loss. So, this is a loss function. This function is giving you a loss function for this particular things. So, we want to minimize this. So, this is a softmax loss, what is defined. I will also define this cross entropy in the next slide. So, let us understand, I mentioned this term cross entropy loss actually. So, what is meant by cross entropy loss? So what we consider, so there are in the ground truth, you have a probability distributions. And usually we have hard probabilities, hard assignment. Say you have for a sample, suppose you have a sample that you have an object, input object, and consider now you have two classes. So let us consider two classes. So there are two output you are getting, and each one is generating that value. Each one is generating this value, which is let me consider that by using softmax we are converting into probability, which means, say if the value here is if I put it as say S1 and this is S2, say S1 is the value, this node is for class 1 and this node is for say class 2. So the corresponding softmax probability would be e to the power S1 by, as we have said, e to the power S1 plus e to the power S2, and this one would be e to the power S2 by e to the power S1 plus e to the power S2. Now this is the model we consider. So this is you can see that if I sum these two values, it would be equal to 1. That means you are getting a probability at this point, and this is a probability at this point. Now the thing is that, so this I will be writing as probability of this node, and this is the probability. So if I write it as P, this will be basically 1 minus P for the two classes. Now when you have the ground truth, now one of these class, say for of this object, the ground truth may be for omega 1, say it is belonging to omega 1, then we say that the probability to omega 1 is 1 and probability of omega 2 is 0. So when we say the cross entropy, cross entropy between, so this is the probabilistic distributions, this is the probability distributions which is given to you, which is the ground truth, and it could be any arbitrary values also, like it could be some q and 1 minus q, but in the case of typical examples, let me consider either it is 1 0 or 0 1, they are hard values, and these are the probabilities. So when you take the cross entropy, you know that if it is a single entropy, if it is a normal entropy, and entropy measure is P of log P minus P of log P, and if you have k classes, so I equal to 1 to k. That is the measure of entropy that we have already learned. So entropy tells you that how flat is the distributions. So if it is very skewed, entropy would be low, and if it is uniform, the entropy would be high. So those are the interpretations of the entropy. Now when we say a given distribution, like if Qi is the ground truth, then what we will consider? We will consider the cross entropy would be Qi log Pi, sum of Qi log Pi. But you note that, which means that in this case, if it is value is 1, if the value is 1, then Pi value should be high. Then Pi value should be very high. Okay. Then you are basically trying to minimize this problem. Then the entropy would be small. But if this value is small, so for that, that means Qi equal to 1. So when you have label, the labels is either 1 or 0. So you write it either y and 1 minus y. That's why you are writing, say y is the label. Then for the other class, 1 minus y is the label, and there y belongs to, it is already mentioned, it is y equal to 1, 0. So that's why we considered this. So suppose this class is 0, so level of y is 0. So we take the probability of log 1 minus p would be considered, and suppose this is level of y equal to 1, then we will just use the log of p for that class. So this is what is cross entropy, and this loss you are going to minimize. So if we can extend it for multi classes, this is the multi-class expression, and we can see that how multi-class expression is the same multi-class expression. So, instead of Qi, we are written here YOC, that is the level. So, YOC is the level of that corresponding node given the class. This is the ground truth. So, binary indicator 1 if O belongs to C, else 0. So, you know that this estimates the probability of O belonging to C, and here you are using softmax probability. So, this is a more general expression which I also discussed previously. So, this is a true probability of O belonging to C. O is that node. O is that respective output node. For the regularization loss, as I mentioned that we penalize the complex models. So, there are different kinds of mathematical expressions which will consider this term. One is that weight decay regularizations using the L2 norm. So, you can see that sum of square of all the W, all the weights, individual weights, that gives you a value. So, if your this value, smaller value means those value of the weights are, that's I should say simpler model, that is I. Similarly, it could be instead of sum of square, it could be the absolute values, or you can consider a combination of these two. So, there are different ways this regularization loss could be there. So, how to find best weights once you define the loss function? As you understand now, again you have to search the weight in the parameter space, which means it is an iterative optimization procedure. Start with any initial weight value, then compute the gradients at that point given the input data, then you move along the steepest gradient, opposite to the steepest gradient direction. So, this same backpropagation algorithms is mostly used in this case. As I mentioned, initialize randomly W, then you compute the gradient and move downhill a little bit in the same way as we discussed earlier. So, updating the weight, and you know that alpha is the learning rate. So, when we consider backpropagation, just as a summary, we discussed these things in details in the previous lecture. Just to mention that, recapitulate that part. In backpropagation computation, first you have to make a forward pass computation, so that you know the functional values at our output values at each node of the neurons, and then use them in the backward pass to compute the gradients from the output to the input directions. Now, let us try to understand that what kind of neural architecture you would be suitable for learning the feature extraction. As I mentioned that earlier, I indicated already that actually what we learn the filters, because it is the convolution operations which processes an image and provides the certain characteristics, local characteristics of the images. So, essentially it becomes a convolution with a mask or a kernel. So, let us again assume that the kernel size is 3 cross 3 and the kernel is defined by the respective weights in its the corresponding arrangement has been shown in 3 cross 3 matrix form. So, if I take any particular point and then take this 3 cross 3 neighborhood around that point, then what we are computing? We are computing the product or weighted sum of its neighboring values, and weights are taken from this kernel. And what are the neighboring pixels we are considering? There is also order. So, which means around say this is, if I consider this is the xy directions along this point xy, and these are the neighbors. This is the neighbor at unit distance, then these are the neighbors. So, you see that x minus 1, y plus 1, which means this neighbor. So, W1 is multiplied with these values. Similarly, W2 is x, y plus 1. So, W2 is multiplied with this value. So, the kernel's positions of the weights, it determines also that which neighboring pixels to be considered for this multiplication, and it is weighted sum of those neighboring pixels that is considered, including the central weight. That means the central weight that also determines the including, and then this gets mapped to a pixel value of the processed image. So, For example, this could be a processed image which are extracting say H pixels from there. So this computation we can express, we can represent this computation in the form of a neural architecture. So you just look at this, this is the same perceptron node except the nonlinearity part. I am showing only the weighted sum part, and these are the respective kernel weights, and say this is the neighborhood pixel. So these are the nodes. So every pixel value, every pixel location is a node, and pixel value is the corresponding excitation input value at that node. So these are the nodes, and so when you are performing, when you are multiplying, you are multiplying with these weights, these nodes, and then the corresponding output. So from these weights, these are the inputs, and this is the corresponding weight. Say if I consider, say this is my location, and maybe this is the position for say x minus 1, y plus 1 position, which is in our case say W1. So this weight is W1. Similarly, this weight is say W2, this is W3, and in this way these weights are assigned corresponding to the kernel's weight. And then those weighted sum is expressed in the form of a perceptron node, that is a neural node. And you can use of course a bias later on for a general model, but in this case simply it is a weighted sum, and that is what is the value of convolution. And so the weights defined by a kernel that defines this connection, and this is a convolution. Now you consider at every point you are doing the same thing. So one of the things you should note that in this architecture it is sparsely connected. So earlier we talked about fully connected neural networks. That means fully connected nodes. That means all the input nodes are connected. But now it is not so. Only a localized portion of the inputs that is connected, and that's why the connectivity is sparse. So we theoretically, which means the weights are 0 for all other nodes. So we call this connectivity sparse connectivity. The other thing is that these weights are shared. So once you have defined these weights, at every node this connection is defined in the same way. So your description of the model becomes smaller. The size of the model becomes smaller because it is sufficient to describe this architecture simply by this set of weights, which is 3 cross 3. For its 3 cross 3 kernel, which is simplified 9 parameters. For a fully connected connection, from every pixel all the weights are to be described, and it should be described for every node. So you see so many number of parameters we have used there. But in this connection, in this convolutional architecture, we simply consider this, and this is what we want to do because that is the equivalent of convolution operation. So with this, we can define the convolution layer, architecture of a convolutional layer of a neural network. So you consider some input image, say in this case we have taken 32 cross 32 cross 3, which is a color. You can consider it's a colored image. There are 3 components, and then we define a kernel which is 5 cross 5 cross 3. So it is basically the 5 cross 5 kernel which is repeated for each plane. So each plane is independently computed. Each color plane is independently computed. That is what is used with respect to this kind of computation. It's up your model. So you are describing your model as per your convenience, but you also keep certain generality in that model, right? So this kernel, so filters always extend the full depth of input volume, which means if I use for this 5 cross 5 this component, then if I consider another component here, say for the same 5 cross 5 component is also here, it remains the same. So convolve the filter with the image, that is slide over the image spatially and computing dot product. So that's the same thing what I mentioned. That means using that convolutional architecture of a processing using neural form, you just do it. So this is what you are doing it. So as you can see that now you are connecting with a neuron, So there are the results of taking a dot product between the filter and a small chunk of the image would be something like this. It's a 75 dimensional dot product you are doing, which is equal to this. Actually, this is for each pixel. Yeah. So what you are doing, you are using all the no, you are, as it was said, that throughout the depth you are doing it. So you are doing dot product of all the values, and that means your input excitation also is of 5 cross 5 cross 3 localize these values, and those filter weights are, though they are repeated, they are used, and finally it is 75 dimensional dot product. And in a general model also you introduce a bias. So your filter is a bit more generous. In the normal convolution, in the weighted sum, this B should be equal to 0. But we have generalized the model because we will be learning for the sake of your better, making the model more powerful, you have introduced the generalization. So at different values of B, you may get a better output, better fitting. So locality is one aspect, and it tends to have a local spatial support because as you know that in the previous diagram I showed that some object is placed, say if you have an image, then say this region has some object, this region has some object. So that's why when you are computing using these local excitations, it is trying to capture the characteristics of pertaining to that object only. So that's why the locality is one of the requirement while processing this kind of operations. Then weight sharing I mentioned, and finally the output what you get, that is that we call activation map from the convolutional layer. So there are so many neurons. So actually there are 28 cross 28 neurons for corresponding to each one. So that means the boundaries, we are not processing the boundary pixels which does not cover the entire space. So leaving out those boundaries, and sometimes you can do that also assuming your boundary is padded with zeros or some other values. But in this case, we consider that we are just processing those pixels which has all the neighboring pixels around it, and then it performs that weighted sum and gets the values. So it makes the translational invariance and object appearance is independent of location because of this locality operations. So now you have considered, say this is one filter, but in your model there could be many such filters. That means you have used one 5 cross 5 cross 3, you can use another 7 cross 7 cross 3 filter, and assuming that boundaries are also taken into, so that the sizes become same. But whatever you do, you can use number of filters and each one will give you an activation map, and we call it channel, but all the channels or all the activation map should be of same size. That means its row and height should be same. So accordingly, you should perform this operation. So for green filter also, we are using term green, it is basically a different kernel, we just called it green. So in an abstract form, we can say that, for example, in this case, let there be 6 such filters, which are each one of is 5 cross 5 cross 3, which means each one will produce the same size of activation maps, and the stack of these activation maps, that itself becomes the next output of the next. So it should be the input to the next layer of processing. So it is that level of, this is one level of representation, and again you can process it by using same process, by using similar kind of convolution operations, which is depth-wise convolutions, and you can get the activations of the next stages of processing. So this actually continues. So the features of convolutional layer, if we look at it, summarize it, I mentioned locality, then translation invariance, and then the weights are shared. And each unit is applied to all locations. Weights of filters are also invariant. That means invariant to locations and invariant to, So each unit output of filter is connected to a local rectangular area in the input. And this is called also receptive field. that local area, what is covered for a particular pixel, central pixel, for which you are computing the convolution. So, that area is called receptive field. Now, in your model, you introduce another kind of generalization, and which is at par with the artificial neural networks paradigm, that there has to be a non-linearity at the range, because this non-linearity is required, because as you understand that I mentioned that through matrix algebra you can define the input-output relationships. Now, if because of the non-linearity you cannot make it you cannot just simply make it associative. If you could make it associative, then you can multiply all those weight matrices and can represent them by a single composite matrix. So, all multiple layers could be equivalently performed by a single layer. So, there was no gain in increasing the depth of the neural network. But by introducing nonlinearity, so you are providing your model to respond with increasing depth. So, one of the nonlinearity which is commonly used is called ReLU nonlinearity. So, let me just show you different kinds of nonlinearity which are popular here. We know about this sigmoid function, we have discussed, this is a nonlinearity. ReLU is a rectified linear unit, and I have mentioned about this also. As you can see, this is a response, which means if it is positive, x is positive, then it outputs x, but if it is negative, it outputs 0. It could be also tan hyperbolic x. So, you look at all these two things, see, in sigmoid and tan hyperbolic x, it is trying to capture the transitions from -1 to 1, and also it tries to keep it smooth. Now, this is transition from 0 to 1. For sigmoid, transition from 0 to 1, and from tan hyperbolic x, it is transitions from -1 to 1. So, you know that for tan hyperbolic x, the expression could be written in this form: e to the power x minus e to the power minus x, then e to the power x plus e to the power minus x. This is the expression. As you can see that if x tends to infinity, this value would be 1. If x tends to minus infinity, this value would be -1. Whereas, if x is equal to 0, then this value is 0. So, we have a continuous function. There is another interesting nonlinearity which is called leaky ReLU, which means that even at the negative zone also you have some kind of continuity. This is also continuous, but as you know that its differential value is 0 at every point, but in leaky ReLU you have also non-zero gradients, and which is also in the negative directions. So, you have non-zero gradients in the leaky ReLU operation. So, a convolutional neural networks, it's a sequence of convolutional layers and nonlinearities. We can consider something like this. So, this is what is a convolutional neural network. And as you understand that feature extraction takes place through these convolution operations, and it goes through at different levels of processing. One of the thing it also performs, I mean, there is also another kind of layer which is there, that is called pooling layer. I will come to that. Before that, let us understand that what is the number of parameters which are involved in this layer. Now, if we consider that your input volume is of size, say W1 cross H1 cross D1, then number of filters k with size this, and with a stride means you are living. So, earlier you are computing at every pixel, say I am computing the convolution value at this pixel, also I am computing convolution value at this pixel. So, we say the stride value is 1 in both horizontal and vertical directions. So, so this is say the direction for H, and this is the direction for W. So, SW is 1, similarly SH is 1. But now, suppose I am computing convolution at this point, and then I am leaving out in this point and computing convolution at this point. So, my SW is equal to 2, that is stride 2. So, what we get? We get a subsampled, in your output, your activation map, size of your activation map reduces. So this striding operation also, see, it is acting like when you are doing the scale operation, say when you are performing that Gaussian pyramid representation, if you remember that we perform downsampling after performing certain filtering. So it is acting like a downsampler, equivalent to a downsampling. And another feature of convolution, as I mentioned, that boundaries, how the boundary values are considered. So you may assume that there are zero padded on both sides. So it depends upon that what is the width of this padding, these are called PW and pH parameter. So with all these things, the output volume, you can show that output volume can be, that means your effective, the size of the width, height and depth. Depth remains the same because you are performing all depth wise operation identically, but width and height, they are dependent upon the number of padding layers and also the stride. As you know that stride will downsample. So if SW is 1, you have the same value, but this is the zero padding. So that's why if you don't have any zero padding, your size would get reduced, width and height, and if you have strides, it would be basically resolution would be also reduced. So the parameters of the weight of the particular convolution layer would be, say, if there are a filter size of FW and FH and D1 is the depth. So single filter is this one, and if there are K filters, you multiply this case identical structure, filter structure. Then you just multiply with K. So many weights, and at each neuron you have K biases for each one you have K. For each filter basically you have K biases. So these are the parameters. So dth depth slice of output is the result of convolution of dth filter over the padded input volume. So if you have K such filters, there would be K channels as the activation map or K activation maps. Each activation map, there is another term we use often, we call them channel. So these are the standard term, and you should know the definitions just to understand the respective literature and discussion. I was just mentioning about pooling. Actually, other than performing strided convolutions, you can directly pool, you can directly reduce the size by doing some, we call it pooling, which means actually sampling the corresponding pixels. We do say one of the pooling operations could be max pooling operations. So you can see in this figure I have shown that if you have an image, say 224 cross 112 size, each image component is reduced to its half, 112 into 56, which means each 4 pixels, 2 cross 2 pixels is mapped to only 1 pixel. And this mapping could be that it is a maximum of those 2 cross 2, whatever pixel values are there. So that is called max pool. So to reduce the amount of parameters and computation in the network, we do it, and to control overfitting. So pooling partitions the input image into a set of non-overlapping rectangles. So, and for each, usually it is non-overlapping, again, which means that there is a stride concept in pooling, but stride could be equal to 1, it could be also overlapping. Usually it is non-overlapping. And for each subregion, outputs are aggregated value of the features in that region. It could be maximum of those values of these respective partition, or it could be average of those values. So there are 2 types of pooling. One is maximum pool value, that max pooling, another one is average pooling. And it operates over each activation map independently. Like the convolution also, you see that convolution filters operate independently, each channel. Pooling, when you are defining pooling, each channel is computed independently. So this is example, this is one example of pooling, just to explain that how this computation goes. Say you consider this is a single depth slice, and you are pooling it. So you partition into 2 cross 2 filter size. So this is a 2 cross 2 filter size, say this one, and then this is another partition, then this is another, this is the 2 cross 2 partitioning. So when you consider max pooling, you consider this value, then this value, and this value, and this value. So your output would be this. You can see that this is the result of the max pooling operation. So how many parameters which are involved in pooling? So once again, you can consider your input volume size is W1 into H1 into D1, which is width is W1, height is H1, and the depth is D1. So if I write something like this, say this is W1, this is H1, and there are D1 number of components or planes or channels, whatever you say. And then pool size is FW cross FH, and with stride, as I mentioned, the partition, it could be also overlapping. So output volume size is defined in this way. So we assume SW and SH is same in these cases. So these are relationships of the pooling but how many parameters are there? You have seen that we have not used any weight or anything to define it. So actually you do not have require any parameter. It is 0. So when you perform pooling in your network, you are not optimizing with respect to any weights. Simply you performing this task. So that is what you are doing. And uncommon to use zero padding in pooling layers. So this is also another thing. So with this, let me stop here today, and we will continue this discussion of deep visual learning. And thank you very much for your patience and listening.